locally testable codes. And connection to cosystolic expansion. Okay. מלך. אוקיי, תודה. אוקיי. Cool. So, I'll start with some kind of motivation and background about PCPs. Maybe a lot of you know about it, but it would be nice to connect it to other stuff we talk about in this course. And then I'll move to describing locally testable codes. We actually saw an example last time. Okay. It's better? Okay. And we saw the linearity testing, and it's an example of a locally testable code. We will put it in that context and talk about other locally testable codes. And then I will talk about another specific example, which is testing of tensor codes. And that will be today. Kind of we have in mind in the few weeks future, this will be a basis to talk about construction of other locally testable codes, as well as we will talk about the quantum LDPC codes. But we won't be able to do everything today, so that will be done later on. Next week I won't be here, and we have Yotam Dickstein, who will give a lecture, and he will describe construction of a high-dimensional expander. So far in this course we just talked about these things abstractly, and next week you will actually get to finally see an honest-to-God construction of a infinite family of simplicial complexes that are bounded degree, and they have all the nice expansion properties. So that's really awesome. Okay, so let's begin. So PCPs, these are probabilistically checkable proofs. It's very hard to write checkable proofs. So what are these? In general, the theory of proof systems is something that developed significantly in the past several decades. Starting from very basic proof systems that you learn about in school, like if my kids learn how to prove various geometric theorems in Euclidean geometry on the plane by writing a sequence of either things from the input or axioms and using derivation rules. And there's a very simple kind of verification procedure to check that this proof is actually correct. And in fact, these days they have an app where they need to enter their homework, they write all the steps, and then the compiler or the verifier, or whatever you want to call it, checks that their homework is correct. I was very impressed by this. So that's one kind of a verifier, right? And in general, for every language in NP is defined to be all those languages that when you are given a solution, there is a polynomial time algorithm that checks that this solution is correct. So we view these as a collection of problems or a collection of proof systems, where if you're given a problem, the theorem that is really being said there is that this three-set instance is satisfiable. It's a statement, it's a theorem, not really, but it's a statement, and the proof is the satisfying assignment. So in that sense, NP is like a collection of many, many proof systems. And that's the most basic kind, where there is a proof and then there is an algorithm that goes over the proof and checks it. But there's many other notions of proofs. You have certainly seen them, interactive proofs, you add randomness, you add rounds, you talk about the query complexity, you talk about the efficiency of the prover and the efficiency of the verifier. So there's many aspects to proof systems, and this is really a kind of a very active area. And one of the success stories within this area, I mean, a lot of the development here is triggered by cryptographic applications where we do have interaction and we have randomness and we want efficiency and all these things. One success story is the notion of a PCP. A PCP PCP verifier is like an NP verifier, but where you become very kind of stingy. The verifier is very efficient. It doesn't need to read the entire proof. It only reads a tiny part in the proof that it selects at random, and we have some promise about that. So we have a situation where so I'll say, okay. So we have some language L in NP. So this is a language, like, for example, that you can keep in mind is like a 3-colorability, or maybe 3-sat. So this is the collection of all graphs that are 3-colorable. This is the collection of all 3CNF formulas that are satisfiable. One of these. And then you get some X, which is supposed to be in the language, and you want to know whether it's in the language or not. And the verifier doesn't just need to read X, it also gets some proof. So there is some, let's call it a witness, pi. It's some string, okay, I don't know, some length. And then the verifier reads X, V is for verifier, and it reads pi, and it needs to say, you know, yes or no, true or false. Okay, and what guarantees do we have? So we call them completeness and soundness. Completeness is that if X is in the language, then there exists some proof such that the verifier says yes. Okay, let me call it yes and not true and false. And soundness is saying that, well, if the theorem or the statement is incorrect, X is not in the language, then for every pi, the verifier will say no. Right? So for example, if the input was a 3CNF formula, 3CNF formula is like, you know, X1 or X2 or not X3, and then you have other clauses and so on, and we call this a 3CNF formula. So suppose this is your input, you want to know if it's satisfiable. This is an NP-hard problem. So of course, what is a proof? A proof is an assignment to the different variables, and it's easy to check it. And if it's satisfiable, there is a satisfying assignment. And if it's not satisfiable, every assignment that the prover will give, the verifier will check it and find out somewhere that it's not being satisfied. Okay, so that's not PCP. In the PCP world, the verifier is more restricted. In the PCP world, we don't just say for every pi the verifier says no, but rather V, let me say it reads only O of 1 bits from pi and chosen at random. There's of course some interesting distribution going on there. And then in the, so this is in the PCP world, and then so the input is some X, the prover gives pi, and then the verifier reads some constant number of bits from the proof, and we are guaranteed that if X is in the language, then there exists a pi such that no matter what randomness the verifier tosses, the probability that the verifier let me just say that the verifier says yes is 1, and if X is not in the language, then no matter what the proof is, we want to say that the verifier says no with probability 1. Of course, since the verifier only reads a tiny part from the proof, this is too much to ask. So instead we say, well, let's say that the verifier says no with probability 1 minus S, and this S, we want it to be 0, so this is the part where it says yes, it's supposed to say no. So this is called the soundness error. Okay, so everyone here saw these things or not? People haven't seen it? Okay, everyone has seen this. Cool. Okay. So I want to kind of describe this in a language that's more similar to high-dimensional expansion to try to highlight the similarities and why these things are related. So really what this means, the PCP version, is that the verification procedure, the verifier can be made localized, so it only reads a small part of the proof, and randomized. So another way of saying it is that there is a PCP compiler that takes, for every language there is a PCP compiler that takes the input and constructs from it something that can be verified locally. Actually, let me see for a minute. So let's take it as an example, 3-SAT. Okay, so 3-SAT, I have a bunch of clauses, x1 or x2 or x3, x3 or x5 not or x7, and so on. So suppose I have n variables, so I have n variables and m clauses, and suppose I want to construct a verification system for 3-SAT that is localized. This I can certainly, and randomized. So the suggestion would be this. So here is a PCP verifier, right? So just choose so given phi. So this is a 3-SAT formula. 3CNF over n variables and m clauses. Choose a random clause, so a number between 1 and m. And then, okay, so given an assignment, I'll call it pi. Basically, pi is just an n-bit string, which is supposed to be an assignment to the n variables. Choose a random clause and check that pi satisfies this clause. Right, so the prover gave us some assignment to all the variables. We want to check if indeed this formula is satisfiable. Choose one of the random clauses and plug it in and see if it's satisfied or not. So what will this verifier achieve? Well, if the formula was in the language, then there is a pi that will cause this verifier to always accept. I'm looking over here. What about if X is not in the language, so this formula is actually not satisfiable? There is no satisfying assignment. I want to understand whether the second part holds, whether for every assignment the probability to say no is at least, well, 1 minus S, I guess. If I didn't define S, it's true. So I claim that this is a PCP verifier with completeness, so we saw, that's good, and soundness, 1 minus s, for which value of s? So firstly, I want to say, for s bigger than 0, that's for sure, because, sorry, for s smaller than 1, I want to say. So it means that there is some probability to say no, right? Because if the thing is not satisfiable, there is going to be at least one clause that is going to point out that this assignment is bad, and so there is going to be some positive probability that the verifier will indeed find this bug and say no. But it would be nice if I can say that S is, but what we want really is to say that S is bigger than some number, I don't know, half, or maybe S is bigger than, I don't know, 0.99, or even S is bigger than 0.0001. Even I'll settle for this, but for some constant. Sorry, that the soundness error, S is a soundness. This is what I, wait. I got me confused by the soundness error. So I want the soundness error to be small, and even this will be fine. Even this, meaning what happens when S is smaller than 0.99? Let's just check that I didn't make a mistake. That the probability to say no is at least 0.01, right? So it depends on the formula, right? If the three-set formula is such that it's unsatisfiable, but it has an assignment that satisfies everything except for one clause, this could be, then I don't even get this, right? I just get S to be 1 over the number of clauses. So I'm saying generically, S can be as high as 1 minus 1 over m. So this is not good. A PCP verifier will have S bounded away from 1 by a constant. Okay, so that's what we want. Right, so let me write it here, I guess. PCP theorem. I don't know if I want to state it now or state it. Okay, let me just say, for every language in NP, there exists some, maybe I should even write it here, there exists some S soundness error less than 1, such that for every language in NP there exists a compiler. I'll call it a compiler, but just think of it as an algorithm. This algorithm kind of encodes encodes input in L that takes X, which might or might not be in L, and as input, and outputs some 3CNF phi, which is really phi of X. Okay, so this compiler, it takes inputs in this language, so it's 3-colorability, and it outputs 3CNFs. But these 3CNFs are not just any 3CNF, they have this special property that if X is in L, then phi X is satisfiable, and if X is not in L, then phi X has this property that for every assignment, there is a good fraction of clauses that reject, that are unhappy. So for every pi, phi of pi, let me write it, phi of pi, the weight of this thing is at least, what should I say? It says no, at least 1 minus S. Right? This is consistent. Okay. So when I write weight of pi, what I'm thinking of a 3CNF formula as a function that takes n bits on n variables and outputs m bits. Right, so it outputs for every clause if it's satisfied or not. So I'm thinking of this formula as a function from n bits to the syndrome, kind of saying for every clause if it's happy or not. And then the weight of phi of pi is just how many clauses are unhappy. Right, so this is the PCP theorem. Okay. Okay, so in general, there are several kind of parameters that people care about in PCPs. One is the witness length. So here, what's going on? You start from some language in NP that has some NP verifier, meaning that for every x in the language there is some witness with some length. Even if we start from 3SAT, then we start with a 3SAT formula over some number of variables n, and this compiler generates a new 3SAT. This compiler runs in polynomial time, or maybe I should have written here polytime. Generates a new formula that is over a larger number of variables, possibly. So it's like an encoding. You start with some 3SAT, and you end up with a new 3SAT that has this extra property, and what the proof length is saying, or the witness length, is how longer is the witness length compared to the initial problem. Okay, so witness length is so for many applications, of course, you want this extra PCP property, but you want the witness length to not grow too much. So it's an open question to whether there can be PCPs that increase the witness length by only a constant overhead. Currently, we know of PCPs that move from witnesses of length k to something k times polylog k and make constant number of queries. Okay. Another interesting parameter is the query complexity, meaning how many bits does the verifier read from the proof, and this comes together with the soundness error. You want the error to be as small as possible while reading as little as possible from the proof. Now, the places where PCPs have been studied the most are in the hardness of approximation. And specifically, I want to talk about a specific domain of hardness of approximation, which is called CSPs, constraint satisfaction problems. And the second domain that people are now extensively studying PCPs in is even related to more practical things that have to do with blockchains and trying to actually implement practical proof systems where you can do very efficient verification. So let me talk a little bit about hardness of approximation. This has been a really productive area where, people in complexity, we like to study computational problems and try to relate the complexity of the problem to the structure of the problem. And CSPs is a special class of problems where this has been very successful. So you have a lot of work looking at the specific CSP and from it deducing the complexity of the CSP. So let's talk about that a little bit. So firstly, I want to say that since what is the relationship between PCPs and hardness of approximation? So I want to make the following claim, that the PCP theorem implies that there exists some constant alpha less than 1 such that it's NP-hard to decide if a given 3-sat formula is satisfiable or at most 1 minus alpha satisfiable. If I use the terminology from before, I want to know if there exists pi such that phi of pi is the weight of phi of pi is 1. All the clauses are satisfied. Wait, did we denote weight to be how many are not satisfied? So 0. All clauses happy. And at most 1 minus alpha satisfiable means that for every pi, the weight of phi of pi is at least alpha. Okay, so at least alpha fraction of the clauses are going to reject. Okay, so my claim is that the PCP theorem implies that if you're given a formula, it's hard to decide between these two things. And why is this true? Maybe someone can say related to what's going on here. Okay, so how do you prove that something is NP-hard? You do a reduction from something else that's NP-hard. So suppose you start with an NP-hard language, and you take an input, and it's NP-hard to decide if this X is in L or not. You run this PCP compiler, and you get this formula phi of X. Now, I'm claiming that for this phi of X, it's exactly NP-hard to decide between these two things. Suppose I had an algorithm that decides for that phi of X between these two cases. Well, if I was in this case, it means that phi of X is satisfiable. It means that X is in the language. And if I'm in this case, it means that phi of X is far from being satisfiable. It means that X must be out of the language, right? So I need to just choose this 1 minus S to be that alpha. Is this clear? You guys are a bit mellow. So there cannot be a polytime algorithm that approximates the value let me call it opt of phi, which is really the value opt of phi, which is the largest fraction of clauses satisfied. Meaning, if you take a formula, maybe it's not satisfiable, but you want to know what's the assignment that satisfies the maximal number of clauses. So you do a maximum over all possible clauses, and the fraction that you get, this is opt of phi. So in this case, opt of phi is 1. Opt of phi is really just equal to 1 minus the weight of phi. Just a different way of writing it. So when everything is satisfied, the fraction is 1.
The minimal weight. You go over all the pies.
You go over all the pies?
Yeah, but it's not written. No, we didn't define the weight of phi without a pi.
Oh, thanks. Okay, 1 minus, thanks, minimum over pi of weight of phi of pi. Okay, and it's also equal to the maximum over pi of, I don't know, okay, whatever, the fraction of clauses satisfied by pi. Okay, so why, okay, so what does this have to do with having no approximation algorithm for this value? Because if I had a very good approximation algorithm for this value, I could distinguish between the case that this value here is 1 and that this value here is less than 1 minus alpha, right? If the value is some number less than 1 minus alpha and I had a very good up to 1 plus alpha approximation, I would run the approximation algorithm and it would allow me to distinguish between this and that case, and this is NP-hard. So this is why, this is how kind of the PCP theorem, which we view as a proof system and so on, is really related to a hardness of approximation. And a very interesting theory evolved around trying to understand for different CSPs what is exactly the hardness of approximation threshold. So here is two theorems of Hastad. Given a three-set formula, it's NP-hard to decide between the opt of phi is 1 and opt of phi is less than 7 over 8 plus epsilon. This is for every epsilon. So not only it's hard to decide between 1 and some number less than 1, actually the threshold is known and it's exactly at 7/8. And why 7/8? If you have a three-set formula, I'm claiming there's a very easy way to satisfy 7 over 8 of the clauses, right? Do you know this? Just take a random assignment. Since every clause has 3 bits, there's 8 possible assignments, and only one of them is going to be bad. In expectation, you will satisfy 7 out of the 8 possibilities. So in expectation, you satisfy 7 over 8. Therefore, there always is an assignment that satisfies this fraction, because not everything can be below the expectation. And what this statement is saying is that it's hard to decide between you don't know if you're given a formula trying to satisfy 7 over 8 plus a little bit is already NP-hard. That's quite amazing. And another really amazing theorem is the same thing with the 3-ling formula. So a 3-ling formula is like a 3-sat, except instead of clauses of 3CNF, you have clauses of the following form. And so on. The reason it's called 3-ling is because it involves only 3 variables in each formula. This is a 3-ling formula. And again, it's NP-hard to decide between 2 cases. now I want to say opt is 1 and here opt is, I don't know, less than something, but that won't be true because it's actually in polynomial time to decide if a sequence of linear formula is satisfiable or not, right?
Where do the x's live in this setting?
Yeah, let's put them in Z2, so they're bits.
Isn't it linear algebra?
It is linear algebra. It is linear algebra, so this is not going to be NP-hard. It's easy to decide if, but if you put here 0.99 or some 1 minus epsilon, all of a sudden things are very different. Given a system of equations, and you should really think of this as quite overdetermined, so there's going to be more equations than variables. And you're told that there is an assignment that satisfies almost all of them. Please find it. You cannot find anything better than roughly a half. So the theorem of Hastad is that it's NP-hard to decide between 1 minus epsilon and half plus epsilon. Basically between 1 and a half, which is really kind of the worst possible. And it's true, of course, for any, not only if the equations involve 3 variables, but even in this very special case, it's still NP-hard. I think this is quite a remarkable theorem. So let me make a few definitions. Okay, so we define a map phi from n bits to m bits to be q local if every output bit depends on its most q input bits. Okay, if every output bit depends on its most q input bits. I'm not going to formally define what it means depend on its most q input bits. It should be obvious, right? That it only looks at a few of them. Okay, so I'm slowly moving to define what a CSP is, right? So every phi like this that is q local gives me, I can think of it as a satisfiability problem. So the problem phi is, or can be viewed as a satisfiability problem. Decide if phi, if there exists some assignment in 0, 1 to the n, I can write pi, let me write a, such that phi of a is, okay, let me say the all zeros. There's slight, I wanted to be all zeros to be consistent with what we did before in the cohomology, but usually in computer science 0 is false and 1 is true, so I should also maybe write all ones. But the point is, I want it to be so that, let's for now define that on the right hand side of these equations 0 means true, so this is supposed to be true, and the bar means for every m. Okay, so the satisfiability for phi is just to decide if this is if there is a satisfying assignment, and we define sat of phi to be just the set of the inverse of the all zero string, which is just the set of a's such that phi of a's is the all zero. This is like okay. So this is just a definition. You know, if phi is also a linear map, could be, right, that it's just a linear map, then this is the same as the kernel of phi, right? When phi is a linear map. Okay. So what kind of CSPs do people study? The way the theory of the complexity of CSPs evolved is to look at these Q-local maps and classify them according to which predicate is being applied. For example, 3-SAT, there is an OR predicate on 3 bits, and 3-LIN, there is some modulo 2 predicate. So in general, a predicate in this context is just some function from Q bits to 0, 1 or to true false, and also overloading this notation, we think of a predicate as being maybe a collection of some. Let me use it. Of some predicates. P is a predicate family. So for example, for 3CNF, I have 8 predicates. One of them is X or Y or Z. One of them is not X or Y or Z. The other is not X or not Y or Z. And I have 8 of them, 8 possibilities. Negation patterns. Right? And if I take P to be these, then for these specific predicates, the kind of local maps that I get are exactly 3CNF. So I say phi is a P CSP if phi is a function from n bits to m bits to m bits, such that for every input, for every output bit, for every one of the output bits in M, the rth output is computed by a predicate P and P on some Q input bits. Sorry?
What is the R?
Just for every R. So for every one of the output bits, the way it's computed, so maybe I just, these are the input bits over here. And every output bit depends on some Q input bits. And how does it depend? You apply some predicate. It's a PCSP if all the predicates you apply come from the specific family P. So in the case of 3CNF, all you do is you add some negation pattern and you do an OR. This is a 3CNF. In a 3-LIN, you XOR and then you either add 1 because you want X plus Y plus Z to equal 1, or you don't add 1. So you have 2 different predicates if you want. And in general, you can study this for many different families of predicates. And depending on the family, these numbers, this completeness and soundness here changes, right? We see already that for 3CNF, we have 7/8, and for 3-LIN, we have a half. And this would lead you to conjecture that the correct number, at least the number here, should be maybe the probability that a random assignment satisfies this predicate, right? Because a random assignment satisfies half of the linear equations, and it satisfies 7/8 of the 3-SAT formula, but that's not correct. So it's correct for some large class of predicates if they are pairwise independent. But in general, the story is much more complicated, and I'm not talking about it in this course, but if you care about it, it's a really very developed theory, and there is a famous unique games conjecture, which if it's true, it implies that we have a pretty nice understanding of this theory, meaning that if it's true, in some sense, we know the correct gap for every predicate. you should take this with a grain of salt. Okay. So now let me define what it means to be a robust CSP. Okay, so I want to capture this property that was good for the PCP theorem. And the property was, when I have some local map and I have some potential assignment to the variables, there's two natural measures I can look at when I look at this assignment. One, how close is it to a satisfying assignment? This is really what I care about. And two, how many of the output bits are actually satisfied? How many output bits are zero? Okay, so there's two measures. One is the weight of phi of A. So I'm looking at some A an assignment. And one thing I can look at is what is the weight. So how many times the output bit is unhappy? And the second thing I can look at is the distance of A to the set of satisfying assignments. Remember what, did I erase it? No, here it is. Remember we defined this set to be all the assignments that satisfy all the clauses or all the checks. Okay, so I can look at these two measures, and it's H robust if these things are related. So if the ratio is always at least H. Okay, and I'm writing it this way because it's supposed to remind us the definition of systolic expansion, where I'll write it in another color. In systolic expansion, we had delta, delta I went from Ci to Ci plus 1. And on one end, we had some chain here, so F belonged here, and then we looked at delta I of F. We looked at the weight of this thing. So delta I is like this phi. On one hand, we looked at the weight of delta I, and on the other hand, we looked at the distance of F to the kernel of delta I, right? So we type, everything looks the same here. Weight is weight, phi in delta. I guess let me call this A, why not? I'm allowed to change this letter, so I call it A. So this is an I chain, this A. So on one hand, I'm looking at this I chain and I'm computing the delta, I'm checking how many times it's 0, and this is how many times it's not 0. And on the other hand, I'm checking how close is it to an actual element in the kernel, meaning someone that when you map it, you get actually 0. And this is exactly what's going on here. On one hand, we take the assignment and we calculate phi. We check how many, 3 set clauses are unhappy. And on the other hand, we're asking, okay, how far is it from an actually satisfying assignment? I mean, what's the difference? In the denominator, we ask how many bits do I need to change in A to make it perfectly satisfying? Okay, and it could be that, for example, phi is totally unsatisfiable. So I'll define it so it's convenient to define by convention a distance of some A to the empty set. I mean, this set could be empty, right, if phi is unsatisfiable. So we define this to be 1. Okay, so it could be that this is unsatisfiable, so there's no number of bits you can change to make it satisfiable, but it could be that that phi of A is actually very, very small. Only one clause is unsatisfied. So these A's are like problematic. They're kind of the ones that make this very, very small. But if there is some H where H is constant, it means that whenever I manage to satisfy almost all the clauses, I must be close to a satisfying assignment. Okay, so kind of a way to prove the PCP theorem is to say, for every, I have an algorithm that for every language in NP, it works on input X and it generates a 3-set that is robust. And then, if X was not in the language, it must be that this is 1, so this robust formula will have the property that all assignments violate a lot, and in the use case there will be a satisfying assignment. So that would be like a way to prove the PCP theorem. It's actually stronger, but I want to say that it's of the same flavor. Okay, so now let's take a break, and after the break we'll move to talk about locally testable codes, which is basically continue to talk about the same thing, but now reduced to the case where phi is linear. And the reason we care about this is because I mentioned the PCP theorem in some applications of it. What I didn't talk about is how to prove the PCP theorem, and empirically, the way we know how to prove it goes through this notion of locally testable code. We want to take our NP problem, our X, and make it into this robustified local map. And the way we do it, this encoding or this compiling, we use locally testable code. So, okay, let's take a few minutes break.
Recording in progress. Recording stopped. Recording in progress.
Okay. All right. So let's kind of summarize this and leave it for now. Basically, I wanted to say that all the time so far when we talked about coboundary expansion and coboundary maps, we always considered linear maps. And these linear maps, they start from the I-chain, say functions on the edges of a simplicial complex, and they compute functions on the triangles. So inherently, a triangle only has 3 edges in it, so these are very local maps. The value at every output bit depends on only 3 input bits, or if it's I+1 chains, the value at every point here depends on I+2 bits in the input. So these are very local maps. And a more general situation is to allow some map. And we also talked about a chain complex where you just have vector spaces, maybe A0, A1, A2, and so on. And we defined what it is to be a chain complex, and we wanted that delta is 0. But also here we talked only about linear maps. Here we are talking about some arbitrary, not linear maps, but we still retain the fact that they are local. Okay? So focusing on the locality, this has to do with the fact that the PCP verifier only is going to look at a very small part of the input, the assignment, the witness, whatever it is. And one way to view the PCP theorem is that it allows you to take any map and compile it into a local map. Okay, that's even the Cook-Levin theorem allows me to do that. Not only local map, it's also something like a robust map. It's true, there has been a sequence of papers proving that indeed you can do this. You can compile any polynomial time map into this kind of map, but this is stronger than the PCP theorem. PCP theorem is something along these lines. Anyway, how do you do these things? How do you prove such a statement? So as I said, suppose you wanted to prove the PCP theorem. You would start with your favorite NP-hard problem, say 3-SAT, and you want to do a transformation that takes any 3-SAT formula and as input and outputs a new 3-SAT formula, maybe over a larger number of variables, with these properties that there is a relationship. If the input is satisfiable, the output is satisfiable. If the input is not satisfiable, the output is kind of far from satisfiable. The opt of the output will be small. In fact, if you want to prove Haskel's formula theorem, you need to prove that it's going to be no more than 7 over 8 plus a little bit. And how is the proof for this theorem? The first thing you do is you take your input formula, which is, it's a 3-SAT, so it has variables x1 to xn, and it has some clauses, phi1 up to phi m. These are the output bits of phi, and you want to encode them. So first you take these input bits and you encode them using an error correcting code. Basically, you need to introduce some redundancy. So an error correcting code is a good idea. That's one thing. But also you want this robustness. So you want, for example, that the new variables, I don't know, z1 up to zn, these are now, the assignment to these variables is an encoding of the assignment to these variables. But you want to be able to check that this is a valid encoding. So in particular, you want that the fact that this is an encoding is something that your verifier will be able to check. Okay, so you want, so this is in some code, plus a verifier can check membership in the code. So this is a property that you naturally want when you use an error correcting code inside a PCP proof. You want additional properties that we won't talk about today, but I'm saying this is one motivation for the property of being a locally testable code. So I'll define it in a minute. Let me just remind everyone. So a code, I can view a code as a function from 0,1 to the n to 0,1 to the m, a linear function, where this is a linear function and the code is the kernel of this function. So a code, error correcting code, I'm not writing ECC, error correcting code is a linear subspace. It can be given, well, you can specify a linear subspace in many ways. It can be given via a map, we call it a parity check map. We call it a parity check matrix, okay? Via parity check matrix H. So what is H? It's a matrix that has these dimensions. So given some W, a string of n bits, if HW is 0, then W is in the code. So so that C is the kernel of H, which means it's the set of W's in 0, 1 to the n, such that HW0. Okay. Right, so that's one way to specify a linear subspace. And if we have the property that our map H is a local map, what does it mean that it's a local map? That every row, what does it mean that H is a local map? It means that every bit in the output depends on only a constant number of bits in the input. So what is a bit in the output? How do I compute it? I take my W and I kind of take the inner product with the first row. That's the first bit in the output. So what does it mean to depend on a few bits? It means that there's only a constant number of ones here, right? So if H has at most Q number of ones in each row, then it is Q local. And we also call this, then C is called LDPC. LDPC, low density parity check, meaning that the matrix, the parity check matrix has low density, it has a few number of ones. And why is this important? Because if you're given some W, you don't know if it's in the code or not, to compute, to decide this, you have a linear time algorithm, because for every bit you work only constant, you need a constant number of bits in the first row and so on. So you can decide this in linear time, and you know, coding theory is actually used in practice all the time, and linear time algorithms are super important. If you have a quadratic algorithm, it's not useful for huge, you know, when you encode very large strings. Okay. So any code that has a low density parity check is called an LDPC code. And now I can define a locally testable code. So a locally testable code is a LDPC code that has a parity check matrix that is robust. So we'll define this now. I just want to make the following trivial point, but it's important. The parity check matrix is not unique in any way. If I have a parity check matrix and then I take the sum of these two rows and I put it as another row here, it's still the parity check matrix for the same code. So the parity checks, no one said they have to be linearly independent. They can be redundant. So, you know, for example, maybe this was not a correct picture. Maybe I can draw it so that there are more parity checks than bits. Of course, I want there to be words in this code that are non-zero, so I want actually the row rank here to be smaller than n. Okay. And redundancy is actually what will help us. So let me actually put the definition over here. So, okay, I'll write it here. Definition LTC, a code C is a locally testable code with Q queries and, let me say, and LTC parameter H if there is a parity check map H a parity check map H that is Q local, and for every word I have this ratio between I apply the parity check, I get a string of n bits that might not all be 0. So I look at the Hamming weight of this string, and when I write weight, I always talk about the normalized Hamming weight. Okay, so it's a number between 0 and 1, which is the fraction of non-zeros here. And I divide it by the distance of W from the code, and I should really say, no, let me not, okay, I'll write it like this. For every W that's not in the code, okay, this is bigger than H, and I can also alternatively write for every W, the weight of HW is bigger than H times the distance of W to the code. So now, if W is in the code, this is 0 and this is 0, that's fine. If W is not in the code, then I have this. So these are equivalent. So it's kind of, this statement says really that this arrow, this H from 0, 1 to the n to 0, 1 to the n, has this consistoric expansion in it. Okay. So, do there exist even locally testable codes? I claim that we saw that the linearity testing is such a code. So let's remember that. And before I say that, actually, so just to repeat again, why is this a useful notion? Because in coding theory, we often get a word W that is not in the code. There is some noise that happened to it, and you want to know if it's close to the code. Now, how will you find out if it's close to the code? There's an exponentially large search space. So if you know that you calculate the parity checks, and if you see that only a few of them are unhappy, then if you're in this situation where you have this kind of inequality, it means that this is small, implies W is close to the code. And what does that have to do with locally testing? The thing is, if you want to know the weight of HW, you don't really need to read every bit in HW. You can just randomly sample a few bits, and it will give you a good estimate. And when you randomly sample a few locations, since every location in HW depends on at most few bits in W, you really only read a constant number of bits in W, and you get this great estimate. So that's a nice thing. So let's look at some examples of LTCs. So the first one is the Hadamard code. Adamar, I should say. Hadamard code. Okay. So this is really the code that we saw. We called it L. It was the collection of all FA, which are strings of length 2 to the n. We didn't write them like this. We wrote them FA from 0, 1 to the n to 0, 1. And we viewed them as linear functions where A is an n-bit string, which is the coefficients of the linear functions. But I can write the kind of truth table of this function, and it's a 2 to the n-bit long string, such that for every x in 0, 1 to the n, FA at point x is equal to summation AI xi mod 2. So that's the definition of this code. It's a subspace of 0, 1 to the 2 to the n. It's not a very efficient code. The number of functions you have here is 2 to the n out of 2 to the 2 to the n. Okay, so the dimension is logarithmic. The dimension is n, and the ambient dimension is 2 to the n. So it's very, very low dimension, but it's a very good code in many other respects. what is a possible parity check matrix for this code? Okay, so I ask you, suggest a parity check matrix for this code. Yeah?
Like for each u and v, so the check that f of u plus f of v is.
Okay, so let's see, what would be the dimensions of this parity check? So like the input will be some potential function f, so the length here is 2 to the n. So I should have 2 to the n over here. And then what is this dimension?
2 to the n over 2.
Well, I will have a check for every possible u and v, right? So there's 2 to the n possibilities for u, 2 to the n possibilities for v, so I have 2 to the 2n possible rows. Each row corresponds to a pair u and v. And there will be 3 ones in this row, in u, in v, and in u plus v. Right? And if you're 0 on every single one of these rows, you are in my code. Okay? Of course, it's a super redundant collection of checks, right? I can think of a much more efficient parity check matrix, but this one is good because we saw that it's a locally testable. It makes this code a locally testable code. So, according to our definition, a code is locally testable if there exists a parity check matrix that's Q local. So we saw that this parity check matrix, well, it's definitely 3 local. That's really nice. And we saw that it satisfies this inequality that we saw that, what was the theorem we saw? We saw that for every W, so we called it F, for every F, the distance of F from being linear is bounded by the fraction, the probability that the test rejects, which is how many of these rows here are not don't sum to 0. So we saw that there was some 2 over 9, right? So there was this was smaller than the minimum between this and 2 over 9. And you can invert it. If you put h to be equal to 9 over 2 or 2 over 9, then you get this inequality. I don't want to get confused on the board, but something like that. So we saw. I guess we had this thing where we said we had this chain. We said z2 to the n. We called it v. We mapped it to z2 to the v, and this we mapped to z2 to the v cross v. So this one we call delta 0, this one we call delta 1. So h being equal to delta 1 makes L and LTC. Actually, an excellent LTC. Okay, so that was one example. What's another example? Very famous example are the low degree polynomials. So let me call it the Reed-Muller code. Reed-Muller code. So I'm looking at all functions. There is some underlying field FQ and some number of variables m. And I'm looking at all functions from FQ to the m to FQ such that f is the evaluation of a degree d polynomial. If you want, you can, right, so a degree d polynomial, it means it's a summation of alpha s pi xi to the si, where s are like m tuples of integers. So s are like in z to the m, well, z non-negative, such that summation si is less than d. Right, so this is a polynomial of degree at most d in m variables. Okay. Okay, this thing, and so let me write f of x equals, so there exists some alphas such that this holds. And if you want, you can think of the map that takes a bunch of coefficients and does this pointwise evaluation as the kind of the generating matrix of this code. And I can ask myself, well, first of all, is it even a linear subspace? Well, clearly, if I have two low-degree polynomials and I add them, I get a low-degree polynomial. So it is a linear subspace. It's not over F2 anymore, it's over FQ, but that's okay. And I can ask myself, what is a good parity check matrix for this code? Usually, we don't speak in this language. We say, what is a good test for something to be a low-degree polynomial? So you're looking at your function f. It's written the value of f at every point. How would you test if it's a low-degree polynomial? And kind of the really beautiful property of low-degree polynomials over many variables is that if you think of the vector space fq to the m, there are many affine lines inside of it. And when you have a degree d function and you restrict it to the points on this line, it remains a degree d. But now it becomes a univariate polynomial. So, if you had the polynomial, for example, xy to the 3 plus x to the 2 times y, this is a degree 4 polynomial in two variables. And if I plug in, say, the line, a line is like a function from a single parameter to two functions. This one should be a linear function, this one should be a linear function. For example, tt. So if I plug in t here and here, I get t to the 4 plus t to the 3. So I got a degree 4 univariate polynomial. So in general, this is true. And the test for being a multivariate polynomial of low degree, it turns out that this is a good test. Pass a random line, check that the polynomial on this line has low degree. To check that the polynomial on this line has low degree, it's more than one parity check. This involves a few parity checks. So I don't want to draw this matrix, but okay, let's look at this rectangle here. The matrix will have a chunk of checks for every different line in the vector space. And okay, it requires some work to prove that this is a good test and so on. We're not going to do it now. Okay. Third example is a tensor code, but keep it well. Some of the examples I will write are examples, and some are going to be counter examples. Okay. So some of you may have already seen low degree tests. So the fact that the Reed-Muller code is a LTC, this is often referred to as the low degree test. And just to tell you, this is a very important theorem that this can be tested, and there are several parameters: the number of variables, the size of the field, the degree, what kind of test you do. And papers are being written on this topic as we speak. So this is a very active area, even though it's been active since the 90s, since the early 90s. I mean, this is really the heart of the PCP theorem, is a good analysis of the low degree test. But even since then until today, we still don't fully understand all the parameters, and there's a lot of action here. What I want to tell you is that inside the low degree test, inside there is the proof, if you've seen it. What you do is you choose a point in your space, and then you choose two lines through it in different directions, and then you look at the plane you look at the plane spanned by these two lines, and then we look at like all the affine shifts of this line and all the affine shifts of that line, and the restriction to this specific situation gives you a tensor code. And then you use the fact that certain tensor codes are locally testable. So kind of at the heart of this thing, there is some local testability of tensor codes. And in fact, this is also true for the Hadamard code. The proof that we saw, you can also view it like that, because okay, never mind why. So anyway, it's natural to try to understand this more basic situation of a tensor code. So let me define what that is. Okay, so given, okay, so let's see. Let's try to do it in order. Okay, if I have two codes, so I have a code C1, which is a subset of 0, 1 to the n1, and its dimension is k1. Dimension of C1 is k1. And I have another code C2, which is a subset of 0, 1 to the n2, and its dimension is k2. The tensor of these two linear subspaces is the set of all n1 by n2 matrices. So actually n1 by n2 matrices, such that every row belongs to C2, and every column belongs to C1. Okay, so I write it like this: C1 tensor C2 is the collection of matrices. It's not going to be nice. I'll write it here. C1 tensor C2 is the collection of matrices in 0, 1 to the n1 times n2. So such that for every A and B, so for every A in n1 and every B in n2, M of A, okay, let me make sure. If I fix A, so it means I fixed one of the rows and I let the second index run freely, I'm a string of length n2, so I should belong to C2. And for this one, I should belong to C1. Okay, so that's the definition of a tensor code. And by induction, it generalizes. You can define C1 tensor C2 tensor CD. And I think for today, so I don't get confused with the indices, I'll just assume that C1 is equal to C2. So it's a special case, but it's just for convenience. Okay, so I want to talk about local testability of a tensor code. Now, what can I mean? So suppose we have two codes, C1, C2. We are looking at a tensor C1, tensor C2. So code word or potential code word is some matrix like this. Okay, you can even, when you say matrix, maybe you think of a linear transformation. This is not a linear transformation. It's more like a table. It's a string of n1 times n2 bits organized in this way. Okay, so you're given this, and I gave it to you. Maybe it has some noise, maybe no. And I ask you, is it a member of the tensor code? What would be a natural test to try to test? Columns and rows. Right, so when I specify this, I should say, choose something at random and then check. So I would choose either a column or a row at random and check that the word restricted to this column is actually in C1, or if I were choosing a row, I would check that this row is actually in C2. So that's a natural check. Okay, I didn't, maybe I should have said what is a parity check matrix for this code, right? Parity check matrix for this code is you basically combine all the parity check matrices for C2 applied on the rows, and also all the parity check matrices for C1 applied on all of the columns. So that will give me a big parity check matrix for the tensor. And the question is whether this kind of random choosing a row or column is a good test for being a tensor code. And the answer is yes and no. The answer is it depends on C1 and C2. It's not always true and it's not always false. When, okay, so let me actually write it. So when C1 and C2 are nice low degree polynomials, then this is actually a good test. This is a theorem of Polishuk and Spielmann from the 90s. Okay, so theorem 1, this is Polishuk-Spielmann. If C1 is equal to C2, for example, is equal to the Reed-Solomon code with degree at most D. So I didn't define this code. This is the code of all, this is like the Reed-Muller code where M equals 1. So it's the collection of all functions from FQ to FQ that have degree at most D. That's a Reed-Solomon code. If both of them are Reed-Solomon with degree at most D and D is less than half minus epsilon times the size of the field. So there is also a size of the field here, right? So let me actually write Q here and less than D here. And D is small compared to the field size. It's less than half. Then the row column test is epsilon squared robust. Did I define robust, or how did we define it? Gives an epsilon squared LTC. Okay, what I mean is that if you tell me that the test succeeds with failed with probability epsilon, it means I'm probability delta. Then it means I'm delta times epsilon squared. Delta divided by epsilon squared close to the code. Okay, so actually, since I'm not sure I didn't define properly, let me just say it gives an LTC. Okay? I'm not absolutely sure where the constant fits in. So one interesting point in this statement is that you see that when the degree goes to half, when epsilon shrinks, the LTCness decays, and it turns out that if D is equal to Q over 2 or above, then the code above, then okay, I didn't write it correctly. Then the row column test, let me write it, is a good test for this code, C1 tensor C2. Okay? And if the degree is bigger than half times Q, then C1 tensor C2 is not an LTC. So what does it mean that it's not an LTC? It means that there is an example of some matrix M that satisfies, well, okay, to not be an LTC, it means there is no good test at all. That's a bit too strong. I don't know how to prove it, but I believe it's true. But what I can definitely prove, then the row column test not good for C1 tensor C2. So that means that there exists some matrix such that the test looks pretty good on it. Okay, so the test seems like it's a good, it succeeds with very high probability, it rejects very rarely. Nevertheless, it's very, very far from the code. Okay, but now I see that I skipped too fast and I didn't define robust local testability. And this is a notion that is stronger than local testability, and this is the notion really I should have been talking about in both of these statements. So let me rewind on that. Okay. To motivate robust local stability, so let me say something about robust local stability, motivating it, and then we can take a break and finish. So these codes, the tensor code, the Reed-Muller code, actually the linear functions code, all of these codes that we encounter when we talk about locally testable codes, they have this nice feature that they are what's called a Tanner code. A Tanner code is like this recursive definition where you already have some small code. Like here, I already know what it means to be a low degree univariate polynomial. This is something I already know. And now I look at functions over some bigger space, so they have more bits, more coordinates, and I say, okay, my new code is going to be all the functions on the big space that on certain subsets of the space, the restriction of the function needs to be in the smaller code. Okay, so also in the tensor is also an example like this. Now I'm looking at n squared bits, or n1 times n2 bits, and I'm saying, okay, who will be in my code? All functions on n1 times n2 bits, such that the restriction to every column is in C1. The restriction of every row is in C2. If C1 and C2 were the same, it would be a more classical Tanner code. So in general, what is a Tanner code? The way people think about it, you look at a bipartite graph where you have here all the bits in your code. So this is n vertices for n bits. And here you have some number of local views. I don't know, let me call them M. And every local view is connected to some number of bits. And also, it's not only a bipartite graph, there's also an ordering, like the neighbors of this guy come with an order, like 1, 2, 3, 4. And then this guy is connected to these 4, and he orders his neighbors 1, 2, 3, 4, and so on. And we say that a function is in this Tanner code if when you label the bits, so basically a function is putting the bits over here on these vertices. It's in the Tanner code if when you restrict to these 4 bits and you look from this point of view, what you see belongs to some smaller code C0. Okay, so a Tanner code by 2 things. So one, you have a bipartite graph, D right regular graph. And the second thing is a small code C0, which is in 0, 1 to the D. Okay, and the code is defined to be, so if I call this A and this B, and the Tanner of this graph and C0 is defined to be all the functions from A to 0, 1, such that for every element in B, the restriction of the function to the neighbors of B is in C0. This is just a formal way of writing it. For every B over here, I look at the neighbors of B, and I look at my string restricted just to these 4 coordinates, and I order them according to this ordering. This is hidden in the notation. And this should be in C naught. That's a Tanner code. And you can see that the tensor code can be defined as a Tanner code, and the Reed-Muller can be defined as a Tanner code, and so on. And interestingly, Tanner codes, they admit a nice composition. Like if C0 itself is a Tanner code, okay, then when you look at the Tanner code with C0 as a small code, but C0 itself is a Tanner code with some C00, you still get a Tanner code, because to know if your word is in the code, you need to look at every vertex here and look at the window inside the word and check if it's in C0. And how do you do that? There's another small bipartite graph that has small windows inside this bigger window, and there you need to check that every small window is in C00. So you can really compose 2 Tanner codes together, and you get, if this one was some Q1 local and the inner code is Q0 local, you get that the Tanner code is actually Q0 local, because every big test is checked by many small tests. So maybe I haven't explained it correctly, but just kind of get the idea. So what's interesting is that you define a code by a bunch of checks. One wonders if these are also good local tests. Is it true that or can you find codes where even if F restricted to this little window is in C0 most of the time, you still end up being close to the code? And turns out that the property of being locally testable is not suited well enough for composition. If you want to compose one Tanner code with another Tanner code and so on, the definition of local testability as it is, it's not good for composition. Instead, the definition that is good for composition is a definition of robust local testability. Okay, so what is that? In the definition of local testability, we were looking, where should I define this? In the definition of local testability, okay, erase this. We are looking at a test that says, okay, I'm given some code word, I read some number of bits, and I check if it's okay, let's even be more specific to Tanner code. What would be a natural test for a Tanner code? It would be, okay, I'm given a string of n bits. I look at my bipartite graph there. I choose one of the vertices on the right, one of those B's, and then I just read the local window corresponding to B. I read all the bits that are neighbors of B, and I check if what I see is inside C0. And I count how many times I'm in C0 and how many times I'm not in C0. That's kind of the syndrome. Another natural thing to do is to say, well, what if you're not, you look at some B, you look at the local word restricted to B, and it's not in C0, so it fails the check. But you know what? It was very, very close to C0. C0 is a code, and there's a difference between some string that's really far from the code and some string that's actually, it's not in the code, but it's close to the code. So a more refined notion would not say, okay, either you're in the code or you're out of the code, and that's all I care about. A more refined notion would say, okay, I'll go over the different small windows specified by this bipartite graph. And for every window, I will calculate not whether or not you're in C0, but actually the distance. How far or close are you to C0? So I'll call this the average local distance. So of course, the global distance is well defined. Given a string, how far or close you are to the code, okay. And now I'm defining this new notion, which is the average local distance. For every local view, let's calculate the local distance and take the average over that. Okay, and robustness, robust testability is like local testability, but comparing these two notions. So we want to compare, okay, so a code is, I don't know, H robust with respect to a given Tanner graph, a given, let me call it a Tanner test. When I say Tanner test, I just mean you select one of the b's at random and you look at the local view over here. So if the I can do this kind of quotient where in the denominator I have, like I always do, the distance of my string to the code, and in the numerator I will have the average. So I'll take the expectation over b. It's the average over taking a random window of the distance of W restricted to the neighbors of B. This is the same notation as here. To C naught, to the kind of the small code. Okay, so it's going to be H robust if this is bigger than some H. So how is this different from what we had before? Before, instead of distance, we had like an indicator variable here. We would say, okay, it's 1 if this is not in the code, it's 0 if this is in the code. And under that definition of distance, this was exactly what we defined to be plain vanilla local testability. And now we have this kind of more refined notion of saying, okay, locally we look at the average and globally we look at the average, and we want these to be comparable. Okay, and really what I should have said both here and here is that it's a stronger statement, is that this code is robustly locally testable with the row column test. So it means that if you look at your matrix that's supposed to be in your tensor code, and you look at every column and you calculate how far it is from low degree, you look at every row and you calculate how far it is from low degree, then the average distance is a good estimate to the distance you are from low degree. And this is only true for degrees up to half, and it's blatantly false for degrees above a half. And okay, let's take a break. You can think of this as a puzzle. Once I tell you it's true, maybe you can actually discover the counter example here. But if not, then after the break we will say it.
Recording stopped.
Let me give an example of the Tanner graph for like the tensor code. Maybe it will help. Okay, so in the tensor code I have n squared bits. Let's say I'm looking at the tensor code of the same code twice. So I'm looking at C tensor C, where C is some code of n bits. So what does the Tanner graph look like? This guy is in 0, 1 to the n squared. It's all these matrices that are n by n. So what does the Tanner graph look like? I have a vertex for every bit in the code. So I have n squared vertices on the left. And I have, how many vertices do I have on the right?
The size of h times 2n.
Right, so I actually have two n vertices. N vertices here and n vertices here. Because in the tensor code, every vertex is in charge of many parity checks. So this vertex, these are the n rows, and these are the n columns. Okay, let me also draw this here so we have this drawing for reference. So this is a row and this is a column. A typical row, so it's connected to how many bits? To n bits, right? So the degree of this guy is n, the degree is n. And every column also has n bits, so the degree of this guy is also n. And what is the local code that this guy is looking at? So this guy is connected, for example, the first row is connected to the first of the n squared bits in a specific order, and the requirement is that the restriction of this n squared long string to this chunk belongs to C. So really C0 here is just this, so so C tensor C can be written as the tenor of this specific bipartite graph, let me call it curly B, with C. C0 equals C here. Does that make sense? Okay, so just an example. And the row column test, what is it? In this, according to this picture, and by the way, what is the degree? What is the degree here? 2. It's only connected to one row and to one column. Okay. So what is the test, the row column test? It's choose a random vertex here on the right hand side of this graph and read all of the bits of its neighbors, so n bits, and check that this thing is a valid code word of C. Now, it could be that C itself is itself a tenor code. Maybe it's also a tensor, maybe it's some tenor code, I don't know what. So when I choose a random column here, and now I need to read n bits and check that this guy is in C. Maybe I'm lazy, I'm not going to do the entire check. I'm going to remember that C is a tenor code itself. So C itself has the same picture, some little curly B of its own, with n bits on the right and I don't know how many tests on the left. And maybe C is testable with Q queries. So instead of checking reading all these n bits, I can now choose a random check for C and read only Q bits. So if C itself is a tenor code with checks of arity Q, I get checks for this code with arity Q in total. Okay, so basically, if I take two tenor codes and compose them, what I get is a tenor code whose locality is as small as the smaller one, which is good in terms of the LDPC-ness, like the parity check, but now we are interested in talking about local testability. And we are interested in asking if choosing a random row and column and looking at what's going on here is a good test, and if it's good for composition. And I'm not going to kind of prove this formally, but the thing is that suppose you want to do this, you want to check that this is a good code by selecting a random, say, column and just checking if the local view is a good code word. And you want to do this by checking that a random little check passes. Suppose you do that. The only conclusion you will reach is not that this whole local view is a good code word. The best thing you can hope for is to conclude that what you see is close to a good code word. Because you only checked some small number of bits. The conclusion you're allowed to reach is that you're close to a good code word, not that you're actually a good code word. And so we want to be able to use that conclusion, which is why we weaken our definition and we talk not about for every B looking at whether or not you're in the code, but rather for every B looking at are you close or not from the local code. So in the break I made some modification here. First of all, I added minimum over W because, over all the words outside the code, because this is really what we want. We want that for every W, the distance, the local distance is a good measure for the global distance. And this is really our test. Our test is select a random B and look at the local distance. And if on average this is small, then having this inequality means that the small local average implies small local average distance implies small global distance. Okay, so this is clear? Okay, good. So now I want to talk again about how to prove a robust local testability. And let's kind of start to prove it. I want to start like an imaginary proof for, I have some code C1 tensor C2. And I have some word M, which is potentially, it's in 0, 1 to the N1 cross N2. And I want to, and suppose I know that this word has small local average distance, so that for a typical column or a typical row, what I see here is close to the row code and close to the column code. Okay? Actually, you know what? To be even more concrete, I don't know if I should do that or not. Okay, so should I do that or not? Yeah, let me actually give another example. The only thing that is kind of annoying when I give this example is that I want to talk about Reed-Solomon codes. So I want this guy to be Reed-Solomon with field Q and degree at most D, and I want this guy to be a Reed-Solomon with field Q and degree at most D. So the only thing is that these are low-degree polynomials over some large field, so they're not bits anymore. The alphabet is FQ. So it means that the code words, I can view them as tables where each element, every bit in the code is not a bit, it's an element in the field. But that's okay. So now M, you can view it like this, but really what's going on is that it's good to index the rows by X and the columns by Y. And how many columns do I have? I have Q columns and Q rows, so X and Y are really themselves elements in the field, and M is nothing but FQ times FQ. So here N1 is FQ, and N1 is FQ. And N2 is FQ as well. So it's N1 times N2 to the alphabet. So I hope I didn't confuse too much. Everything here is FQ. This is FQ, this is FQ, and this is FQ. And what is it? It's just a function, M of XY is a function that that for every Y, the degree in X should be at most D, and for every X, the degree in Y should be at most D. So really the code is just order MXY such that the degree in X of MY is at most D, and the degree in Y of MX is at most D, right? So it's a polynomial with two variables with this degree restriction. And the test is, okay, fix some specific value for X, like 7, plug it into the, if you get the polynomial as a formula, or if you get it as a point evaluation, you fix this Y, and you look at this, and you see, how close or how far is it from degree D in X. Okay, so suppose I'm given this table, and I want to prove this theorem that I stated over there by Polishuk-Spielmann, that if on average a random column is close to degree D and a random row is close to degree D, I want to prove that I can correct this, change a few locations, and make it a perfect degree D, a perfect polynomial with these degree restrictions. How will I do it? a natural thing to do is to define M row and M column, or in more generality, for every local view that I have, so the local views that I have here are the rows and the columns, I look at M and I define for this local view the best possible correct value that is available for me. So if I think about it in this bipartite graph, my capital M is written over here. For every vertex I have a bit or an element in the field. This is capital M, it's written on these vertices. And now for every local view, I look at only the n values corresponding to this row, for example. And maybe it's not a perfect low degree polynomial, but maybe it's all zeros except for one bit. So the best choice is the all zero low degree polynomial. And for this vertex, there is some other choice. So in general, I can define for every row a good element in my code C1, and for every column a good element in my code C2. And this will be my two corrected matrices. M row will be the matrix whose rows are in C2. And this is the matrix whose columns are in C1. Okay, so basically these two things together are the collection of local views, and I can do it in more generality, not only for tensors. Whenever I'm given some code word and I know what the local views are, I can assign for every local view kind of the best choice. Also in the Reed-Muller low degree test, where you have all these lines in many directions, for every line you can kind of choose the best possible value. And what you get is a collection of little functions, like a collection of local views, functions on little local views. And if this was a perfect code word to begin with, all of these local views will be perfectly in agreement, and they will agree with some global code word. But if your initial thing that you started with had some issues, then your local views might not agree. The matrix had zeros everywhere except for a single one. So this row decided to choose the all zeros as the best local view. But maybe in this column actually you had the all ones. So this column actually decided to choose the all ones function, which is also low degree. And so the local views don't necessarily have to agree. And what you end up with is a different incarnation of the same question. It's a bit similar and a bit different, which is you have here a collection of local views, and each local view in itself, it's perfect. It's a low degree function, or it belongs to your code. It's good, but they don't agree. So you have what we call an agreement testing problem. So I'll write it kind of not formally. So given a collection of local views, and right now the way we should think about it is, specifically for the tensor code, a collection of local views means you're given two matrices, the rows local views and the columns local views. Okay, so every bit appears twice, that's why you have two matrices. Given a collection of local views, if suppose they agree often, okay, so why am I assuming this? If my collection of local views came by starting with a single object and kind of locally making these changes, then usually I won't have this situation where this guy wants this to be a 1 and this guy wants it to be a 0. I'll say that again soon. But, okay, actually let me say it now. There is some assumption I need to make about this matrix which will force that they often agree. What is this assumption? It's exactly that the local average distance is small, meaning that for a random column or random row, usually what I see is very close to a correct code word. If this is very close to a correct code word, then the difference between the local view and what is actually here is very small, only in this one point. Okay? And for random column also, the distance between an average local view and I mean the perfect local view and what's written here is very small. So usually when you look at like a random row and a random column, they intersect on one bit, and typically what the rows matrix has here equals what the initial matrix had, and also what the column matrix here equals what the initial matrix had. So the fact that you had small, local average distance means that the local views often agree with each other. Okay. So now we have this assumption: the local views often agree with each other. We want to conclude something from it, so we need to deduce. Then this is kind of testability properties, that if the local views agree with each other, then there exists some matrix M hat in the code, C1 tensor C2 or whatever, that's close to both the rows and the columns. So this is an agreement testing, not a problem, but like a theorem. It holds for some pairs of codes that if we are given this M row and M col, and you know that they agree often, that can only be if both of them are really close to a single code word. Okay, and that's like a theorem, a statement. And this is what Polishuk-Spielman proved. Okay, this is what they proved. They said, suppose, in their case, both C1 and C2 are these low-degree polynomials. You get a columns matrix and you get a rows matrix, and they agree on 1 minus delta fraction of the tests. So the test is to choose a random row and a random column and check. Okay, if they agree on delta fraction of the test, then their distance is no more from an actual code word is delta divided by epsilon squared. This is the precise statement. Okay, I'm not going to write it, but this is the precise statement. And notice that, if epsilon is 1/4, for example, or something, then it's delta divided by, 16. So it's good. Delta times 16, I should say. Yeah, it's delta divided by quarter squared. So delta agreement implies 16 delta distance. That's nice. But once epsilon kind of approaches 0, hoops, the whole thing fails. And actually I have to admit that for years and years I knew of this result, and I thought that it's just an artifact of the proof, and I thought that probably this should hold further for D above a half. But it turns out that there's a good reason why this fails, and actually, so let's see the counter example, right? So I said that if D is actually bigger than half times Q, this is not a good test. And so what does a counter example look like? It looks like two matrices, M row and M col. One has rows that are low degree functions, one has columns that are low degree functions, and they agree really, really well, okay? But they are really far from any low degree polynomial. Okay, they are really far from anything that is in the tensor code. Okay, now I don't want to make a mistake in copying, so I will write it. Okay, so this example is due to swastika party. Actually, I erased this. So it's m of xy is defined to be 1 minus x minus y to the q minus 1. Okay, so what does this matrix look like? When x equals y, so on the diagonal, this is 0, this is 1, so I have 1s on the diagonal. Okay, and when x is not equal to y, you have some element in the field raised to the power q minus 1 is equal to 1. 1 minus 1, you get 0. Okay, so you just get the identity. Not very interesting, okay? Okay, but let's write it as a sum of monomials. So I get here 1 minus, and then I have, okay, I guess it's x to the I, y to the q minus 1 minus I. Maybe I should also put like a minus y here, I don't know. And that's it, right? Summation goes from 0 to, sorry?
There's a coefficient.
There's a
minus 1 over I.
There's a q minus 1, choose I. Thank you. Okay. The point is that I want to arrange this sum as two sums. It's P1 plus P2. Okay, P1 of xy and P2 of xy, where I take all the monomials where I is less than q over 2 and I put it here, and I take all the rest of the monomials and put them over here, but these, for them, when I is bigger than q over 2, then this thing is smaller than q over 2. So basically here I have that the y degree is smaller than q over 2, and here I have that the x degree is smaller than q over 2, right? So I've managed to write m as P1 plus P2, and I claim that this is the columns, this is the m col, because for every fixed y, the x degree is less than q over 2, so it belongs to my code. If I choose now my code to be Reed Solomon with field q and degree equals to q over 2. Okay, so m col, every column is in the code, and this is m row, because for every fixed x, the y degree is less than q over 2, so every row is in the code. So I managed to write the identity matrix, which is a very sparse matrix, as the sum of m rows. So let me I draw it for myself. This indicates that the rows are okay, and this indicates that the columns are okay. Okay, and so what do I have here? Two matrices. Here the columns are polynomials, and when you add them up, or you get this matrix, that means that for a random column and a random row, a random I and a random j, usually j is not equal to I, right? If you choose them at random, you get that they're equal. Okay, so the ith column is equal to the jth row on the common point. Okay, if you choose I and I, then they're actually not equal, so they're not always equal. The fact that they're not always equal means that the first column or the first row, one of them is not 0. They cannot both be 0, right? Also, the second column and the second row cannot both be 0. So at least one of these guys has half of the columns or rows non-zero. So it has a lot of non-zeros, okay? Has a lot of non-zeros. And also the other guy must also have a lot of non-zeros, because this plus this, or this minus this, whatever, is almost 0. So it means that both of them have quite heavy weight, okay? And the only tensor code word that this can be close to is the 0 tensor code word, right? So these have heavy weight, they're not close to the 0 tensor code word, and they're not close to any other tensor code word. But notice that they agree with each other quite fantastically. They agree with each other with probability n over n squared, 1 over n. Really, really high. That's when they disagree. They agree with probability 1 minus 1 over n. Okay, so it's a counterexample to this, to having this agreement test. And as I said, when the degree is smaller than half, actually, this cannot. There is no counterexample. This can be proven. So I think this is quite cool and a very simple example, and this can be generalized. quite a lot, and so I didn't manage to prove, but we know, okay, so we know some more results. We know, I guess I wrote this theorem, this claim, and there's other theorems. We know that if C1 is whatever it means to be smooth, so for example, if C1 is an LDPC, well, let me say expander code. I think we saw those in the first lecture of the course. Then C1 tensor C for any code C is robustly testable. And another theorem is that if C1 and C2 are random, then again C1 tensor C2 is robustly testable. And in general, this turns out to be very important also for the quantum LDPC codes, which we will talk about later on. We don't understand what makes a pair of codes robustly testable, and there is a really nice way to draw this as a chain complex, which we will do next time we speak about this, which really says that robust testability, or this agreement testability, is really a kind of coboundary expansion of this tensor code. Actually, maybe in the remaining 5 minutes, no, I won't do it. So, yeah, let me try to do it, why not? Okay. So we can draw a chain that goes like this. You start from some k squared bits, then you encode to some k by n, where every column of k bits you kind of expand it to a code word. So you basically use the generator matrix on every column separately. We denote it by G tensor I, and you can also do the same for the rows, I tensor G. So you get, for every row of k bits, you expanded it to an entire column like this. And then you can do, if you already did the columns, now you should do the rows. So you do I tensor G, and you get here an n by n matrix. Here you do G tensor I. Okay, so it's clear what I'm doing. I'm taking a k-bit string and stretching it to an n-bit string by the encoding matrix. And now I'm taking every column and stretching it further here. And now the thing is, I can view these guys. What is this object, this k by n matrix? I can view it as m col, because for every, now I'm not thinking of something that came from here. I'm thinking just of this object. If you give me a k by n matrix with a bunch of elements inside, doesn't matter, I view every k-bit column as the code word that it becomes once it goes here. So maybe I should write m col over here. It's like once I encode it, I get a column matrix, and once I encode this, I get a row matrix, right? And now we view this as a two-chain. Really, I have a vector space which is this guy over here. I have a vector space which is the sum of these two vector spaces over here, and I have a vector space over here, and I have a map that goes from here to here, which is what we said, encode, and then I have another map which is encode, and then add them up. So the map here, if I start from any k squared bit string here, and I first stretch the columns and then stretch the rows, I will get the same result as if I first stretch the rows and then stretch the columns. So the sum will be 0. So I get the delta delta is 0. And the fact, you see these two matrices here, M row and M col, these are exactly the matrices we talked about in this agreement testing thing. And this translates, I'll do it much more slowly and kind of more organized when we talk about the quantum LDPC, but this translates to what you need here is exactly, it translates to the agreement stability of this tensor code. Okay, why am I saying this? Because we have a few examples of when a pair of codes have this agreement stability. We know it for random codes, but we don't have any understanding really of what makes a pair of codes have this property. And this is very interesting. Also, if you want to generalize it to a tensor of 3 codes, this is wide open. We actually don't know of any triplet of codes that satisfy the proper 3-dimensional generalization. And yeah, so kind of even for this very simple like tensor, which is not a very complicated expander, we don't understand this once you put these codes on here. So it's kind of something that a lot of people are interested in. And okay,